Environmental pollution and poor air quality have been major global challenges for many years. Iran is no exception, and cities like Tehran face significant impact on public health and environmental quality. A large share of this pollution comes from particulate matter, emissions from fossil fuel combustion, and various industrial processes. Concrete, as the most widely used construction material in the world, is made from cement, aggregates, water, and chemical admixture. Its production and transportation demand considerable energy. Cement manufacturing alone is a major contributor to carbon dioxide emissions, accounting for about 8% of all the human-generated carbon dioxide, mainly because clinker production requires very high temperature and intensive fuel consumption. To reduce the environmental impacts of concrete, supplementary cementitious materials or SCMs such as GGBFS, fly ash, and silica fume can partially replace Portland cement. This typically lowers embodied carbon dioxide and can improve durability by reducing permeability. However, the net benefit depends on optimized sourcing and transportation, since logistic emissions may offset the gains. Silica fume strongly reduces permeability and can increase strength. It often requires admixture optimized and carefully shrinkage, curing control. GGBFS lowers permeability and improves resistance to chloride as sulfate attack. Early age strain may develop more slowly. Fly ash improves workability and can reduce heat of hydrogen and mitigates ASR. Early strain may decrease depending on type and replace level. First of all, a base mix design or BCS was defined based on common local practice, which including 400 kilograms of Portland cement per cubic meter of concrete. Then, according to a competition guidelines, an alternative mix design or ACS was developed, which replaced 40% of the cement with SCMs while keeping the water to binder ratio constant, including 32% slag and 8% silica fume. These two mix designs form the basis for comparing durability and environmental impacts.
Three common transportation methods were considered, including road, rail, and marine transport. Depending on local conditions and accessibility, each method was used accordingly. In general, marine and rail transportation have lower environmental impacts compared to road transportation. The cement used was selected from the Kangon cement plant, which is one of the suppliers for the Tehran city. Crushed aggregates and the admixtures were also sourced from one of the nearest producers. For SCM, silica fume was selected from Semna. Slag from Isfahan and fly ash due to the lack of domestic production was selected from Gujarat, India. The details of transportation routes are presented in the following slides. Except for the mixing water which is available at the production site, all other materials are transported from their factories to the production location. Cement is transported from Kangon by road with a transportation distance of 1,167 kilometers. Silica fume is supplied from Semnan, which includes 22.7 kilometers of road transportation and 227 kilometers of rail transportation. Fly ash was selected from Kutch region in Gujarat, and its transportation route includes 20.4 kilometers by road, 1,587.2 kilometers by the sea, and 1,482.5 kilometers by rail. Slag was sourced from Isfahan Steel Company, and due to presence of a railway station, the rail transportation distance is 622 kilometers, while the road transportation distance is only 5.7 kilometers. Crushed aggregates were selected from the Burjadi quarry with a road transportation distance of 28.5 kilometers. Due to the lack of recycled aggregate production in Iran, the use of this option was not possible. The superplasticizer admixture was also selected from the production site with a transportation distance of 49 kilometers from the university. After applying the transportation distances and material specifications in the Ecoconcrete calculation tool, the environmental impacts of each material were calculated by placing 1 kilogram of each material into the tool. This table provides the basis for comparing the environmental impacts of different materials. Since only SCMs can replace cement, a scoring system of 100 was applied to 4 materials: cement, silica fume, fly ash, and slag. As can be seen, the results show that cement and silica fume have the highest environmental impacts, while slag and fly ash have the lowest impacts. To evaluate the effect of SCMs on concrete durability, a 1% replacement of each material was analyzed using the Live 365 software. The results showed that silica fume followed by fly ash and then slag provides the greatest increase in service life. Considering the high durability performance of silica fume and the low environmental impacts of slag, as well as the availability of both within the country, these two materials were selected to replace 40% of cement. Different replacement ranges from these materials were evaluated in the Ecoconcrete tool and Life 365, and the results are summarized in table shown. An optimization diagram was developed based on the EIR and service life ratio from the previous slide. With the requirement of minimum 15% reduction in EIR, the optimal point was determined to be 8% silica fume and 32% of the slag. For the selected combination, the durability score was calculated to be approximately 3.54. The EIR value was also calculated to be 15.4%. As shown, the reduction in environmental impacts is about 10% across all indicators, reaching over 20% in global warming and fossil fuel depletion. A slight increase is observed in the carcinographic indicator. However, the overall combined effects make it negligible. As a foundation for sustainable development and in accordance with the United Nations Sustainable Development Charter, the development of future infrastructure should be based on innovation and infrastructure, sustainable cities, responsible resource consumption, and the reduction of environmental and climate impacts.